Hello everyone, I'm Yaniv Fogel, and I'm a master's student at the mining department at the University of British Columbia. In the following slides, I will give a brief explanation on frost weathering and freeze and thaw cycles, and how these two natural processes challenge the development of Canada's north. At the end of the presentation, I will describe our approach on simulating these two processes in heterogeneous rocks using a mesh-free numerical method. Northern Canada holds tremendous potential for resource development. Future projects will require immense investments in infrastructure, communications, energy and transportation. One of the major challenges for project development in cold environments is the natural phenomenon of frost weathering. Frost weathering is the deterioration of rock properties due to the effects of extreme cold weather. As the rock deteriorates, open walls and slopes can suffer from frost wedging, rockfalls and even major slides. One of the suspected leading causes are cycles of freeze and thaw that occur naturally as seasons change. But today, there is a growing concern that climate change will have a severe effect on these cycles. Mines, and the infrastructure they rely on, will be vulnerable to these changes, especially when a typical mine life is usually numbered in decades. Over the last century, extensive research was done on the effects of freeze and thaw cycles. Today, the joint action of three mechanisms is suspected to be the main cause. First is volumetric expansion. As water freezes and turns to ice, the volume of the mass increases by 9%, meaning that the water locked in saturated pores and cracks can expand and break the rock from within. The second is hydraulic pressure. As the ice body grows steadily, unfrozen water is pushed to the boundaries, increasing the hydraulic pressure and gradually breaking the pore walls. These two actions can explain simple instantaneous breakage of porous materials, but can't explain the slow propagation of cracks, as witnessed in field surveys and experiments. The third suspected propagator is ice aggregation, or the persistent growth of ice lances in the rock. Ice lances are bodies of ice and are much bigger than the initial size of the pore or crack, hinting that water is able to migrate from inside the rock and towards these lances. This can happen even when the temperature is below the freezing point of water. Current models of crack nucleation and crack propagation simulate some or all of these actions. These models are capable of verifying experimental results, but only to a certain degree. Most of these models are analytical, which rely heavily on linear elastic theories and are mostly restricted to circular or spherical shapes of pores or cracks. Implementation of these models in numerical simulation is limited mostly to continuum-based methods, such as the final element method. But this method can't deal with large displacement and discontinuous problems without becoming computationally demanding. Our approach is to simulate the effects of freeze and thaw cycles in heterogeneous rocks, including crack nucleation, crack propagation, and the formation of ice lances, using the bounded particle discrete element method. The discrete element method is mesh-free, meaning that instead of defining a grid of continuous elements, independent particles are created and can interact with each other. This method is known to better simulate the behavior of granular-like materials. Using a bounded particle model will allow us to simulate the behavior of rigid brittle materials, such as rock or concrete. As analytical models are mostly restricted to circular or spherical crack shapes, using the mesh-free method will allow us to explore simple shapes as well as complex ones. Furthermore, the nature of a mesh-free model allows us to incorporate heterogeneous properties in the model, such as different particle sizes or porosity, simulating the rock matrix beyond the ability of simple linear elastic models. Frost weathering is a complicated subject, incorporating thermal, hydraulic, and mechanical processes. It is our goal that further development and verification of the model proposed here will contribute for future research and understanding of this phenomenon, leading to better, faster, and safer development of Canada's north. Thank you for listening and enjoy the conference.